The video game industry skyrocketed in the 90s. After the development of 3D technology and the ability to take that 3D technology home on a console became viable, a lot of different companies started to take a look at ventures into this area. And before you know it, Microsoft decided to do the same. But the trouble was, up to this point, at least for video game developers, is that they had to work very hard to learn new hardware each time these consoles came out at a pretty significantly fast pace. Now, in the gaming industry, there wasn't necessarily what you would call a cry for help, but certainly developers would probably appreciate a little bit easier of an architecture to learn, or something at least more familiar that could be standardized and used moving forward, and enter the Microsoft Xbox. Microsoft saw the value of using an API that was familiar to programmers, and also continue to build on that as the industry moved along. And they also had hardware that was fairly familiar for programmers to work with. The Pentium core that was inside the Xbox was a slightly customized version of what you'd see of an off-the-shelf PC. So between the DirectX library and the CPU that you'd find similarly to that of a PC, this opened the pool for game development studios to offer more of an opportunity for regular PC developers to get in on the action without having to sacrifice too much time learning new hardware. While it was still there, the learning curve was a lot less steep. And this allowed the developers to focus more on the game design and less on learning the architecture. This also set a new industry standard when it came to video game consoles. It didn't really catch on probably until after the PS3 and the Xbox 360, and the APIs that are exposed are slightly different, but they're more tailored to the general development audience, not these skunkwork or esoteric groups that existed with other video game development. Microsoft took a little bit of a risk going with CISC and taking a little bit more money to develop this system, but in the end, I think it was a tremendous payoff. For those of you who watch my videos, you mostly know me for the hardest consoles to develop on series to try and give you a looking glass window in maybe what it was like to develop on these consoles. Now, while those systems are very interesting to break down and the esoteric nature of them are fascinating, it's also super important to learn about these architectures that set the standard for the industry moving forward, and that's what the original Xbox did. So today, that's what we're going to be talking about. Hi everybody, I'm James from Zygal Studios, and today we're going over a simple overview of the original Xbox hardware architecture. So the Xbox CPU was a Pentium 3 CPU, and the core had a microarchitecture that was configurable like a RISC system. Even though the Pentium 3 was an x86 core, it had configurable microcode that was only accessed by Intel and able to be changed by Intel, that was able to be told what to do by the instructions that were piped to it. And it allowed for some configuration or some ability to change in case of a security breach. But the beauty of this is that this was a similar CPU to that of what you would find inside of a computer at the time, or a PC. And this allowed for more developers to get involved in the action and code to be a little bit more portable between platforms. But that doesn't mean that the architecture wasn't complicated, because it was quite ridiculous in some cases. I mean, the CPU had a 14-stage pipeline. That's insane. A 14-stage pipeline, and it had out-of-order execution and a more complicated approach to predicting branches, which is actually called speculative prediction. But the biggest thing that this offered was the x86 instruction set. In this case, the Intel Enhanced i832 variant allowed for a few specific extensions, a multimedia extension and a streaming extension. Now, these two extensions offered more instructions because, as we know in x86, if you want more functionality, more instructions, right? That's kind of the principle. So this allowed for SIMD techniques, or single instruction multiple data techniques, for multimedia and for specific streaming to the GPU to be allowed with new instructions and faster operation. And the wonderful thing was that the console would have a similar CPU to that of a PC, so if you were programming on a PC, the Xbox would have these same optimizations or these same extensions that you could use back and forth. This here was the best part of that system. Now, as I mentioned before in the intro, a lot of other competitors use RISC systems, and primarily they chose this due to cost and also for learning curves of architectures. Imagine having a esoteric CISC system that had a 14-stage pipeline, and you had to learn it in a month and get a game out in 6 months. Yeah, that's probably not going to happen. So RISC was used to kind of simplify the matter and also make the most of the board space for the compute power for these custom chips so that developers could learn and make good games out of them. The Xbox Original's Pentium 3 core was actually known as what's called the Copper Mine. It had a P6 core with a 32 kilobyte L1 cache and 128 kilobyte L2 cache. The backside bus was at the CPU speed, whereas at the front side bus was 133 megahertz. These were all directly connected to the Xbox's memory controller. The L1 cache was divided into 16 kilobytes for instructions and 16 kilobytes for data, whereas the integrated 128 kilobyte L2 cache just had some general purpose off-the-shelf L2. The front side bus connected the L2 cache with the memory controller. The Intel Pentium 3 CPU connected from the front side bus to the memory controller known as the North Bridge, which then had access to main RAM and the integrated GPU. There was a hyper-transport 8-bit bus that connected the North Bridge to the South Bridge at 200 megahertz. The South Bridge dealt with most of the I/O stuff, so things like USB, SATA, PCI, etc. The crazy thing about the hyper-transport bus was that other PC motherboards had also used this technology, just with a different branding on the name. Connected to the North Bridge was 64 megabytes of DDR SRAM. And in typical old console fashion, we are staring down a unified memory architecture layout. The North Bridge had a switching network, a series of crossbar switches that connected 16 megabyte banks of that 64 megabyte RAM to the CPU and the GPU. This was then controlled by the CPU. This also allowed for more concurrent accesses, and data could be pushed from the CPU to the GPU and vice versa. The NVIDIA NV2A GPU allowed for some pretty amazing techniques and also visuals that you could actually see. It had a 720p mode, which was able to display some pretty stunning visuals. The NV2A was actually based off of the GeForce 3 particular architecture for GPUs, and had a few different sections in its core. It had the command and data, which the Pentium interacted with, as well as the vertex processing, pixel processing, and post-processing section. There was a FIFO that would take in commands from the CPU, and then it would push it to what was called a P-graph, which was the block in the graphics unit that was in charge of graphics processing and other different components that allowed the processing to actually occur. What was interesting is that, much like the flipper processor in the Nintendo GameCube, the geometry didn't actually have to be embedded inside of these commands inside the FIFO buffer. The CPU could actually allocate a buffer in RAM containing vertex data and then tell the GPU to retrieve it from that particular location. This means you wouldn't have to double buffer or copy memory to a temporary buffer and then send it off. Instead, you could just point to exactly where in RAM it was, and the NV2A would be able to retrieve that straight from the main RAM by stuffing the FIFO buffer. Now, due to the complexity of the vertex and pixel processing, I'm going to skip over from that for now and talk about it potentially in a later video. But after all that processing is done, the rasterization needs to occur and be shoved into a frame buffer. There's something called a raster output unit on the NV2A, and it can actually perform tests like depth tests, stencil tests, by using allocated blocks in memory, and then can batch the pixels once they've passed this test. And the frame buffer has the option to be anti-aliased as well. After this point, you can then fill the frame buffer, which then sends it off to the video signal. The standard resolution of the Xbox was at 640 by 480, and it was pretty much standard across the entire generation, including the PS2 and the GameCube. But the GPU could actually physically draw frame buffers up to 4096 by 4096. The Xbox was a pretty darn impressive machine, especially for the time, and basically was like a little PC in a box. The audio processing unit was pretty amazing as well. The audio processing unit was part of the I/O section connected to the South Bridge with the audio controller interface. The audio processing unit had a voice processor, which was a specialized circuit that could synthesize many voices, in this case 256, at a sampling rate of 48K. It had a lot of digital controls to be able to mess around with different voices and things like that. And there was also a global processor that was a programmable DSP that could process the data from the voice processor and apply more effects to it than you already had before. And then, of course, there was an encode processor to compress or comply with different standards in terms of encode and decode. Something to note is that the audio processing unit could only process audio data and compute different things based on it, but couldn't actually output it. And the audio controller interface was the one that actually read the audio data from RAM that was manipulated, decoded, and then sent it to the PCM stereo. This would then create an audio output going through the terminals. The Southbridge system had a lot of peripheral accesses, like 4 USB 1.1 ports, an Ethernet port, an I2C bus that connected a temperature monitor, a double EEPROM that would allow for things like serial numbers to be written to, or MAC addresses, regions, things like that, and also a video encoder, as we talked about before. There's also things to control the external hard drive that would have external storage, and also there was an LPC bus in order to deal with things like bootloaders and production hardware. This concludes a general overview of the Xbox hardware architecture, and like I said, there's a lot more going on underneath the surface, such as a HAL, or a hardware abstraction layer, a lot more going into the game engine side of things, a lot more going into the graphics side of things, a lot more going into the operating system that Microsoft wrote for this, and basically pretty much everything you can think of. So in a future video, or many future videos, I may cover these topics if you guys would like to hear. But overall, the system is very impressive, and I certainly really enjoyed looking into this and learning a bit more about the hardware architecture that the Xbox had standardized with the industry moving forward. If you guys want to take more of a look yourself into all the nitty-gritty details, take a look at Rodrigo Copetti's write-up on the Xbox original architecture. Reading through this breakdown really helped me understand a lot of the hardware behind it, and it's also some of the motivations and the history. His hardware architecture breakdowns are phenomenal, and I use them as research in quite a lot of my videos. I will leave his link in the description below to his personal website, as well as the Xbox entry. Please check him out and consider even subscribing to his thread on his website and donating, because a lot of this information is amazing and needs to be preserved. There you have it, folks. This is the general overview of the Microsoft Xbox hardware architecture. I hope you enjoyed the video. If you did, be sure to like the video. And if you like the video and you want to see more, well, there's going to be more coming in the future, so be sure to hit the subscribe button. And if you had any critiques or any comments you want to leave below, please do so. I'd love to hear from you. And if you have any ideas for anything you want me to cover in the future, also leave them in the comments below. I appreciate all the support you guys have been giving me, and it keeps motivating me to make these videos. This is James from Zygal Studios, signing off.